All right, go ahead and get started. I'd like to wish everybody a happy St. Patrick's Day today, and welcome everybody to one of the IRMCA webinars. This one is part two, Portland Limestone Cement, equivalent performance to type 1, type 2 cement with a smaller carbon footprint. This is hosted by the Illinois Ready Mix Concrete Association. We'd like to let you know that we will be following the Illinois Ready Mix Concrete Association antitrust policy. That is found on the IRMCA website on the webinars pages. Each individual webinar has the antitrust statement posted on it. All these webinars are also recorded. So today's webinar will be recorded and it'll be posted on the IRMCA website as well. My name is Theron Tobalski and I'm the Assistant Executive Director with the Illinois Ready Mix Concrete Association. Some more information we'd like to share is at www.irmca.org. Each one of these webinars has their own individual webinar page. We list all 12 webinars with the dates, times, and speakers. There is a read more option for each one of those webinars that will show all the people who sponsored the webinars. And under each of the sponsors, they have an opportunity to share 3 different links to information that they would like you as the engineers or developers to read. Some of it is on different types of concrete technologies. Some of them is on new different types of pavements that are out there that they would like you to learn about. So I really encourage you to go to the IRMCA website, click on the webinars tabs, and check out all those links. For today's sponsor, here's a list of the sponsors that sponsored today's webinar. Again, if you go on the IRMCA website, you can check out the links that they have posted on there. Today we have 2 presenters. We have Marvin Overmeyer with Bootsy Unisem Cement, and we have James Palmer with VCNA St. Mary's Cement. And I'd like to turn it over to Marvin Overmeyer. He will introduce himself and start our presentations.
All right, thank you. Theron, is that the right screen on your end?
Yes, looks good.
All right, good deal. Once again, I'm Marvin Obermeyer with Bootsy Unisem. I'm out of Indianapolis. My territory includes Illinois and the surrounding states. So many of my states are in the Midwest that I cover. And we're here to talk about Type 1L cement. James works for St. Mary's. I work for Bootsy. We're just 2 of many of the companies that are cement companies. We've been blessed with the good fortune to be able to give this presentation today. And but if you're looking for 1L cement, just contact your favorite cement company. And sooner or later, the cement companies will be coming out with 1L over the next anywhere from 6 months to a couple of years. We're dealing with logistical issues and challenges, silo space, terminal space, what have you. So those will eventually get through. But today's objectives, what we're going to do is we're going to talk about Portland limestone blended cement. And we're going to talk about what is Portland limestone blended cement, how is it made, why to use it, and when does it perform, or how does it perform in concrete. Now, if you don't get a chance to go to a cement plant every day, this is a cement operation in brief overview. And let's see here. All these cement locations, the vast majority of them are located on their quarry. It takes an enormous amount of limestone to make cement. So they can't haul, many times hauling limestone in just doesn't make sense. So bringing the limestone in initially, it goes to a primary crusher. I always joke that you could put a Volkswagen in a primary crusher. Literally can handle rocks that size. And those go down to softball size, down to baseball size, down to marble size. And we spend an enormous amount of energy getting the big rocks down to small pieces of manageable rocks. Once they get down to marble size, they actually go into what a raw mill. This raw mill here is illustrated as a ball mill. That's not unusual. And at that point, the cement plant is looking for a source of calcium, silica, aluminum, and iron. Okay, those four components make up the four components that go into that raw mill right here. Once that the particle size gets down to the particle size of a piece of salt, then it goes into the preheater tower. Most cement plants in this day and age have preheater towers. I think the vast majority of ours, I think James will say the same thing. The preheater towers basically are preheating and drying the material, okay? The material goes through these preheater towers, it goes through these little cyclones. It utilizes all of the heat, the passive heat, if you will, from the kiln over here and from the clinker cooler, which is here. We're going to get to that here in a second. Once that material is brought down here to the final stage, it's already pre-calcined and it's already at about 1,000 degrees before it even goes into the kiln. Once it goes into the kilns range in size between, let's say, 200 feet to 500 feet long and 15 to 20 feet in diameter. They are at an incline so that the material tumbles down toward the heat of the kiln. The heat flame of the kiln is at the business end of the south end of the lowest end of the kiln, of course. That flame is approximately 40 to 50 feet long, maintaining a temperature at approximately 2,600 degrees Fahrenheit. So it's an enormous amount of heat. We basically have lava every day. And it takes us 24 hours. Once we start this puppy up, it takes about 24 hours to get it to optimum temperature. And once the material comes through all the way through the kiln, then it goes to a clinker cooler. Material that comes out of a kiln is not cement, it's actually clinker, ranging in size from golf ball size to, we'll say, marble size, or the size of a marble, okay? These particles are very hot. At this point, they're 2,600 degrees Fahrenheit. So they go into a clinker cooler, which is cooled by an enormous amount of air. The air is blown through the material, and actually, years ago, I'm assuming that this air was wasted, but they capture the air now and put it back from the clinker cooler back into the preheater tower. Usually comes in the middle, and this simple illustration doesn't show that, but it usually comes right about here. And so basically every BTU of heat is wrenched out of that flame, okay? All of it is reused and fully used, and that makes our plants more efficient, which is huge in this conversation. Now, the clinker that's cooled, it's cooled to 300 degrees and then stored in a facility. Here it's showed in a dome. Sometimes it's a dome, sometimes it's a silo. It's a variety of facilities, but once it's stored, then it's blended with a little bit of limestone and some gypsum and put into a finish mill. And yes, this finish mill looks a whole lot like this raw mill over here. As if you were to walk past them at the plant, I'd have to check with our quality manager which one is the raw mill and which one is the finish mill at each one of our plants. Once it comes out of a finish mill, it goes into our silos, and then it can be shipped out in bags, trucks, rail, or barge. Those are the four ways we ship it out. Now, I'm going to take that presentation and twist it just a little bit. When we make Portland limestone cement, the only thing that's different is the last few phases that are highlighted here in this little cloud, okay? 1L blended cement, or Portland limestone cement, also known as 1L, is a blended cement that meets ASTM C595, also meets AASHTO M240. These are the same standards now, okay? And the range of limestone is between 5 and 15% limestone by mass. It's very commonly used in Europe. And that, for this little illustration, imagine one of these had limestone in it, and it would be allowed to add up to 15% limestone. And every cement plant's going to be a little different. Usually have to kind of find the sweet spot because we have to run the finish mills longer because everything's going to be ground finer. We'll talk more about that in a second. And then also, like I said, silo space is going to be at a premium. So we have to designate a special silo at every plant for this 1L, and any one of our 40 different terminals, we have to designate a special silo at that particular terminal. So it's going to be slow to roll out in that regard. But everything else is just a matter of working through the process. Those finish mills look like this. Okay, this illustration on the left shows a finished mill. It's kind of hard to show the scale. These are very large. You can see the stairs on this one on the right to give you an idea of size. Our Greencastle plant, which is one I live closest to, has 3 of these. This particular cut section shows a high efficiency separator. And you'll notice these little steel balls, the dark little steel balls here, and they're smaller over here. That's not unusual, okay? This is called a high efficiency separator. This is where the clinker is coarser. This is where the clinker is finer. Once it gets a little bit finer, it goes through this opening, goes into this section. Once it gets finer enough, it is actually vacuumed or sucked out the exit. That's how it's not conveyed out. It's actually sucked out by air. So the difference between type 1 and type 3 for cement, for example, we may have one of these running type 3 cement only, and we would, the particle size would actually be smaller. So we would choke down that vacuum, so to speak. This is a picture of the inside of a ball mill with a separator, and and this is probably the coarse side. You can see the larger balls. So obviously at this point, it's stopped. It's been stopped for a while because everything has settled, which is kind of a rare picture. That Portland cement that we make every day, that we've been making for years and years, it meets ASTM C150, okay? So in general, there are 5 types of Portland cement, okay? Number 1, 2, 3, 4, and 5. Number 1 is a normal type cement. It's a general use cement. It's very common, only exceeded by type 2, which is moderate sulfate resistance cement. Now, the interesting thing about type 2 cement, type 2 cements, and in order to meet type 2 cement, it also meets type 1 cement. And I think some specifiers get this mixed up, and they'll get a mill report that says 1/2, and they'll think, no, I want type 2 cement. Well, that is type 2 cement. All type 2s meet type 1s. So sometimes if you see a mill report that says 1/2, that means it's a type 2 that also meets type 1. All type 2s meet type 1. Also, there's a note here, it says type 2 MH, which meets moderate heat of hydration. Heat hydration is important when we do mass pours. Any more mass pour, any geometrical area that has the smallest dimension is more than 3 feet can constitute as a mass pour, and where we have to watch our heat hydration and the heat differences in a slab. One of the note, type 2 moderate sulfate resistance has a tricalcium alumina rate limit of 8%. Okay, so the C3A is limited 8% on type 2 cement, whereas type 4 cement, the C3A is limited to 7, and that's low heat hydration cement. Usually, if you see a type 4 cement, those were used back in the day when they built Hoover Dam and all the big structures that were built in the 30s. That's very rare now. It's very, very difficult to find a type 4 cement. Jumping around. Type 3 cement is a high early strength cement. The only difference between, in general, a type 1 and a type 3 is that the type 3 is ground finer, okay? And it will react. It actually has more surface area, okay? And the blane is higher. I'm going to explain that in a little bit. But when the blane is higher, there's more surface area. When there's more surface area, it will achieve higher, earlier strengths. Also will set up faster. Usually used for precasters and pre-stressors or winter applications. Works very well. And actually that product sometimes has a little bit more gypsum in it. I'm splitting hairs. Type 4 is low heat, limit of 7% on the C3A. And type 5, which is also very rare, is high sulfate resistance. Now you'll notice type 2 is moderate sulfate resistance, type 5 is high sulfate resistance. Sulfate resistance usually has to do with wastewater treatment plants or sulfates in the soil. That's usually the two situations we see there. If you take a type 2 and you blend it with a fly ash or a slag, you many times can achieve high sulfate resistance results. Okay, so that's what a lot of the guys do when they have a type 5 application, is they'll blend it with a fly ash or a slag. So same thing with the type 1 cement. Now, we're talking about C595. That's the blended cements. Now we're getting into the 1Ls. This is what we're all gathered to talk about. You'll notice that 1L didn't meet C150. It meets 595 because it's a blended cement. The types of 595 blended cements are Portland blast furnace slag, which is a 1S, and that's a type 1 or type 2 cement blended with a blast furnace slag. And that parentheses for the X, that's usually the percentage of blast furnace slag that's added. Usually that's interground. 1P many times is interground. Portland pozzolan cement, and that is a type 1 or 2 cement blended with a fly ash usually. 1L, that's what we're here gathered to talk about. Portland limestone cement, where calcium carbonate or limestone is added to the cement, and the X value is some number between 5 and 15%. 1T, which you hardly ever see, is a ternary blend where it usually has a fly ash and or a slag. Usually that's the blend there. 1L is limited to a maximum of 15% per ASTM 595. So that means that the parentheses we won't go over 15% there. Usually when we're selling a product like that, we'll designate and tell you what the percentage is for that particular plant. How is PLC different? Okay, Portland limestone cement is made by intergrinding regular clinker with up to 15% limestone, while regular Portland cement contains up to 5% limestone. All right, so let's look at this little illustration right here. All right, this is Portland cement as of today. Okay, they can have up to 5% limestone and still call it a C150 cement. Okay, per ASTM C150. Now you'll notice these particles. This is actually a really good illustration that I think James shared this with me, of course. And these particles are a little bit bigger than these particles. That is not by accident, because as you go from a normal Portland cement to a Portland limestone cement, the cement is a little finer. It is a little smaller particles, and you can go up to 15% limestone. Now, what's that mean? Well, if you go up to these products will, number one, will do a good job of particle packing, very similar to an aggregate packing situation where you have smaller aggregates to work around the larger aggregates. Same thing here. We have small particles of limestone that has a moderate calcium silicate hydrate reaction, but you have small particles of limestone amongst particles of cement. This is a microscopic view of that occasion. This is calcium silicate hydrate. These fingers that are reaching out are calcium silicate hydrate fingers. Now, as you can imagine, one of the things we tell our contractors is do not put too much water in your concrete, because you separate our little buddies away from each other and they can't reach out and touch each other. All right, well, that's what's going on here. If these are too far apart, the calcium silicate hydrate bonds are only going to go so far. But if there is a particle of limestone in there, they'll reach to that and be able to touch base there, just like this situation right here. These are cement particles right here. And then this is the hydration process where calcium silicate hydrate finger bonds are being built, and they can reach to this, this limestone particle. It was another way of looking at, and so since these bonds are shorter, they actually are stronger. It's very similar to if you took a pencil and you broke it, and then you tried to break it again, and the sections keep getting smaller and smaller and smaller, it's going to get to a point where you can't hardly break it. Same here. When these bonds are shorter, they'll be stronger. So that's how nucleation works. All right. from a performance standpoint, engineered for equivalent performance. What that means is when our plants were making a type 1 cement and then they go to a type 1L, the goal there is that that 1L meets or exceeds the performance of the type 1. So now, obviously, as we roll these products out, I always encourage everyone to check for your strengths and your plastic properties before and after. I'm sure everything will. This shouldn't, usually it's beneficial for a lot of the other parameters, permeability, because we have smaller particles here. Heat of hydration might be this all should be very similar, but obviously always check. Alkali silica reactivity should be very good, but always check. Sulfate resistance should be the same, or if not better. So now I want to talk about blame. Not everybody works at a cement plant and works for a cement company for 20 years. So we're going to talk about blame, and I want to explain it first. Okay, it's the units for blame on a mill report are square meters per kilogram. Okay, so let's imagine for a second that all of these little blocks here are particles of cement. Okay, so obviously they're very small, but we're looking through a microscope. These are particles of cement, and let's assume for a second that these particles of cement equal 1 kilogram of weight. Okay. Now, if we were to get our measuring device out and our micrometer, we could determine the surface area of all these cubes. That would be our square meters, our area function. And then kilogram. So if we have 380 square meters per kilogram, that is our blame. Okay. What if I took one of these particles and I cut it in half? Now, I didn't affect our weight, but I affect our surface area. Now we have two new surfaces to fill. These two new surfaces require paste in the world of concrete, but it's more surface. So if we took all of these particles and we cut them all in half, we would have more surface area, which would mean that the blame would be higher. The number would be higher. Okay. Well, that's what we're talking about here. The first set of charts, Portland cement is 380 is the blame, which is in square meters per kilogram. Okay. So that's our surface area of that cement on that day for that run. Okay. And you can see the 7-day, the 1 day, the 28 days. The 28 days are the green numbers, for example, the green bars. And the water cement ratios are basically the same for all these. Okay. And then we made Portland limestone cement. I shouldn't say we. This is data from actually, I think, PCA. But they made Portland limestone cement at 3 different blames. So they increased or made it finer to 450 to 500 and 580, which actually 580, you're at that point approaching type 3 cement fineness. Okay, my rule of thumb is going to be about 600, give or take. So 450, you can see what happened on the 28 days, a little bit lower. 500, it was higher, and this is even higher yet. And you'll notice that the really big difference is the early strengths. Once again, the old adage, the finer it is, the faster it will react. And that's why these numbers go right up at 24 hours and 7 days, same thing. So a good illustration of what's actually really going to happen. The 1Ls will be ground finer, and you'll get better reaction there. Acceptance by state DOTs. This shows a map, like my area geographically is kind of like this. And anyway, to make a long story short, all of my states have approved the use of 1Ls as for DOT work. The areas that are in light green means that they are planning to accept it, and the areas in yellow are they're considering it. Okay. All right. Do your specifications. Oops, timeout. Do your specifications. Something happened on my screen here, guys. Do your specifications allow type 1L? Many specifications accept a Portland limestone cement, ASTM 595. most national standards accept 1L. ACI and the Federal Highway Administration accepts 1L. So little bit more and more, we're seeing more use of 1Ls in the area. In the cement section, look for, if you're looking for specs, look for 595 1L. Near, and also usually it's located where you see anything for C150. ASHTO requirements, if it's ASHTO spec, you're looking for 240, which is going to be close to M85. M85 is what is the same as C150, and M240 is the same as 595. If you're not sure, contact your cement provider. I know James could help his customers. I could help mine. Anybody else on that list, they've got representatives that could help you out with that. Greenercement.com is a really good website that has a lot of information about 1L. That's going to be, that's already been rolled out. That's actually put together by PCA, the Portland Cement Association. As far as example specifications, we've put together a quick and dirty sample specification. And this is kind of an all-encompassing. I didn't go into type 4 or type 5 cements just because I wanted to keep it simple. But you can see that type 1, 2, and 3 meet ASTM C150. And then the blended products, 1P, 1S, 1L, and 1T meet 595. It's that simple. So what you're looking for is you're looking for the 595 and the 1L in this conversation. Okay. Now this is, once again, this is not necessarily specific to PLC, but while not specific to 1L, the following practices are recommended. Number 1, requiring trial batches to confirm. In other words, don't just take 1L, throw it in a mix that you had one type 2 in last month and turn the crank and deliver it for 400 cubic yard job. I always tell customers that if they want to try something new or try a new mix, certainly the earlier you get a chance to get your hands on it, check your air, check your yield. I've even gone so far to work with contractors to go out in the field. We'll make a batch of it, throw it in a wheelbarrow, and have a contractor on the job or at the plant and look at it and give him a trial and say, what do you think? Do you like it? You know, because this is what we're going to make for you next week. If you don't like it, tell us now. When additional requirements, verify the specifications allow for performance-based methods. What we're talking about there, Illinois DOT does allow for performance-based methods. What we're talking about there is instead of going to a type 4 or type 5 cement, adding the fly ash to a mix or a slag that will allow us to get there. Also, the uses of 1L HS, which would be high sulfate, the uses of these products that are more available and allowing us to do it that way. A lot of times our customers can save a nickel, the owner, the DOT can save a nickel. It all makes sense to work together. So, and also those provide durable related benefits. Okay, James, that means you're next.
Thanks, Marvin. Just give me 1 second to share my screen here. All right, can everybody see my screen and cursor?
Yes, looks good, James.
Thanks, Theron. So, yeah, Marvin gave a great overview of kind of how the cement is made and where the specifications come into play. I'd like to remind anybody, if they've got any questions, feel free to type them in to the text field and share them now, and we'll come back to those at the very end. I'm James Palmer. I'm a technical services engineer with St. Mary's Cement. I cover Illinois and Wisconsin primarily, but I also cover portions of Indiana and Iowa. So like Marvin, all of my states, the DOT level at least, the 1L is currently accepted. So moving on to, so why is Portland limestone cement important? You know, why are we talking about it today? And the biggest answer is it's better for the environment. It reduces CO2, which is the most significant factor for improvement with concrete. Looking through, this is basically a global usage of various commodities. And you can see that concrete is number one on this list. And remember here, we're talking about concrete. Concrete and cement are different animals, even though they're often referred to using the same nomenclature. So more than oil and coal, more than asphalt. The only commodity that is used more than concrete is water, and water makes up a percentage of concrete. So that kind of gives you an idea to the scale of which we're talking about. 10 to the 10 is, I believe it's tens of billions of tons per year. So it is basically by using the Portland limestone cement, it's a great opportunity to significantly impact the total CO2 emitted to the environment. When we talk about CO2 emissions in the environment worldwide, concrete is on the order of 5% of all CO2 emissions. Looking at these materials a little differently, we've got the embodied energy on the bottom and the embodied CO2 on the vertical axis. And as you can see here, this is cement, which we are the guilty party for emitting that CO2. But remember, cement and concrete are different. Cement typically only makes up about 15% of concrete. And that is why, pound for pound, concrete actually has more favorable benefits to the environment than many people think. Pound for pound, it's even lower embodied CO2 than timber. And it's basically on par with asphalt. The other benefit of concrete, however, though, is it has a longer service life. Therefore, over the life of the project, you may pave a parking lot a couple times over 40 years, whereas if you've got a concrete parking lot, it goes in there once. So all of a sudden now, asphalt used 4 times is going to move your total CO2 for that parking lot up here, where concrete now looks more favorable for the environment. Marvin gave a good overview of how cement is made. So we're going to go back and touch on that. So where does that CO2 that comes from concrete, where does it originate? And when we're considering concrete, we're looking at the concrete itself, as well as the fuel that goes into your excavators to mine the limestone, the energy used to drive conveyor belts and equipment. What comes out of the flame is also going to contribute, as well as the grinding operations, the energy for those, the transportation to its final location. And that's just from the cement plant side. But again, the biggest contributor to the CO2 is actually coming from this calciner tower that Marvin went into a little more detail on. Basically, as you cook limestone, which is calcium carbonate, CO3, as you cook that, essentially, you've got CO2 that calcines and burns off and leaves this stack as CO2 gas. For every ton of clinker that you're going to make, just under half of that, or excuse me, just over half of a ton for each ton of cement is going to go out that stack as CO2. So to make 1 ton of clinker, you have to burn close to 2 tons of limestone in the kiln, and that CO2 is released. So that is where PLC is able to make up that difference and reduce that CO2 emissions. So this is basically a quick review, but remembering that the cement only makes up 15% of concrete, it helps reduce that picture overall, so that 15% of the concrete, but of that 15%, 60% of the CO2 emissions are coming from calcine. Looking at what that correlates to in terms of cement, this is various cement plants on the bottom. Each plant is different and has to deal with their own raw materials and may handle things slightly differently, but overall, the drivers for our business are similar among all cement plants. So looking at Portland cement, you see a normal type 1-2 would be the blue, and the Portland limestone cement, or your type 1L, would be the green. And just talking about why we prefer PLC when we refer to type 1L, we kind of want to encourage that nomenclature, because if you're used to going to the terminal and picking up type 1-2, and the driver says, I want some type 1L, it's easy for that L to get lost, and we want to eliminate potential sources of loading the wrong material onto our customer's truck. But as I said, about 60% of the total CO2 is coming out of the limestone. So that brings the total kilograms of CO2 from per kilogram of cement down from about 80 to 85% with your type 1-2 product, down to roughly 75 to slightly over 75%. So you're seeing a net benefit of 10% reduction of CO2 by using the Portland limestone product. So CO2, when you're buying concrete and people are ordering concrete, usually nobody's concerned with how much CO2 is being used. You want 4,000 PSI mix. You may want heat of hydration or sulfate resistance. But usually CO2 does not become a factor unless you're dealing with very specific projects. Those projects tend to be driven by a certain number of players. Those green initiatives like LEED and things like that would drive CO2 to be a consideration, driving the cement selection. With that said, the general public is becoming more and more aware of the damaging effects of CO2. So there are starting to be some smaller and even residential customers that when they're building something, they want to do what's right for the environment, where PLC is an appropriate choice. And as Marvin said, PLC is an equivalent product. It's engineered to be equivalent. That said, if you're engineering for equivalence, we've engineered to meet or exceed. So in some cases, there are actually performance benefits with the type 1L product. So how does that matter to you guys? And as I understand it, a significant portion of our audience is engineers. Basically, if you're dealing with a project that requires these green initiatives, you will typically be aware of that fact. And there will be like a lead associate or somebody in such a position that is responsible for gathering all that information, and they should be contacting you and letting you know what information you need to provide. That's where we come in and we can help myself and Marvin as representatives of our respective cement companies. We can find those appropriate documents and help you with that process when those requests come through, but usually it's not something you're going to have to think about. So these are a number of those greener initiatives that you might see. The most popular one in this area is the USGBC, which is Green Building Council, and that is who publishes the LEED standard, which I believe it's Leadership and Excellence in Engineering Design. A second, had that written down.
Leadership in Energy and Environmental Design.
Energy, and I knew energy was in there somewhere. Thank you, Marvin. Basically, if USGBC is involved in the project, it's a good indication you might need to be aware of these things. But as I said, for your run-of-the-mill projects, the things I'm going to talk about next are not things that you should even have to worry about. And typically, you're going to see those on projects that are done for these various organizations. For instance, I think a lot of you would be familiar with, if you're building a government building, there is typically a requirement that there is some level of green initiative included. You'll also see it from various schools, for instance. Anything with EPA, obviously. So these are the things that when you're working with these customers, just be aware that they may come into play, but it should be made very clear in the specification. And then moving on to what's driving cement companies. This is the Architecture 2030 numbers, but internally as cement companies, we also have our own internal initiatives. I know St. Mary's is currently working on the 2050 version. We're looking to get to net zero carbon neutral basically by 2050. And we've still got a ways to go, but PLC is essentially the next step in reducing those CO2 emissions. Over the past, 30, 40 years, there have been various improvements in cement plants. The process that Marvin explained earlier is for a dry process, which is how most cement is made in the US these days. And essentially by not having to boil off water, there's been energy savings and CO2 reductions associated with that. The calciner, the way that is linked to the clinker cooler and the kiln exhaust, reusing those energies, that has also helped to reduce to some extent the CO2 we're emitting. In concrete, the use of SCMs, that's your fly ash and your slag, those also reduce the overall embodied CO2 in the product. So the next step is 1L, which should give us another approximately 10% reduction in CO2 emissions in concrete. So I talked about when these CO2 becomes a consideration, and those are those green initiatives. When those apply, one of the more common things you'll see is your customers will request EPDs. And all EPDs is basically a method for conveying information. The EPDs don't necessarily mean one product is better, but they contain the information to allow consumers to decide between two products if they care about certain aspects such as CO2. And it's essentially a cycle. You report the information, engineers can evaluate based on that information and make selections. And there's continuous innovation and improvement, which kind of leads to the cycle here for completing the EPDs and other aspects of your green initiative assessment. So EPDs are basically like food labels. The presence of the food label doesn't mean it's good for you, but it lets you look and see, I need to watch my fat. This one has less fat. I'm going to buy product B over product A because I can see it has the important qualities for me. Similar to EPDs, but more rare, is LCAs. LCAs are life cycle assessment. It's basically taking your product, in our case concrete, and looking at everything that goes into it over the entire life cycle, from when the limestone was in the ground and those contributions to the building materials used to construct your building, and even including things like disposable when appropriate. So the LCA will take a project and it will consider, if we used the standard type 1-2 cement in our mix, we would emit a certain amount of various products such as CO2, and then comparing that information for doing the job with an alternate product, in this case, PLC. Not all projects are going to have LCAs. Frankly, most projects do not even require EPDs, and LCAs are even less common than that. When LCAs are used, you should definitely be working with a lead energy associate for the project. It's their responsibility to do those things. You're just responsible for supplying that information. So if you're being asked for more than that, by all means, have a conversation, consult with your cement supplier, and we can help navigate those waters, which can be confusing the first couple times going through them, but there's definitely people here to help you with those aspects of your project. And then this is just an example comparison of the global warming potential aspect of the life cycle analysis. As we said before, ordinary Portland cement, this is your type 1-2, you're typically looking at about 1 kilogram of CO2 per kilogram of the product, of which 60% is from the calcining. With the PLC, you see the 10% reduction. The other interesting thing here is this SC represents slag cement. So slag cement, it is a SCM that improves various factors of the concrete and has in the past actually reduced the CO2 content, even though that's not why it's being included in the mix. But if you really want to push the envelope and further reduce your CO2 reduction, those SCMs, secondary cementing materials, can further reduce the impact of your concrete on the environment. And then similarly, this is just looking at the energy. And again, there's a little bit of benefit with PLC, and slag cement and is going to have significantly lower emissions and can be used to complement your mix and improve those properties. So coming back to what that means for the environment, in the US, and this is going back to, I believe, yeah, this is 2019 numbers, but basically if if all the type 1-2 cement that was used in the US had been Portland limestone cement, the CO2 that would not have been emitted to the atmosphere would have been 8.1 million metric tons. So roughly 9 million US tons of CO2 could have been kept out of the environment. Now that's 100% transition from type 1-2 to PLC. It's going to take some time to get there, but that is the direction the industry is headed. In the US, it's likely most of you haven't dealt with PLC, but it is not a new product. It's been around for years, going back to the late 1980s and such was the first time I saw any documents from that time frame. But it was adopted in Europe and Canada in the 2000s, around 2012, I believe Canada started up. So they've been using it for 8 years now. And currently in Canada, at least I know, Portland limestone cement makes up about 50% of the total cement usage. So after 8 years, they've transitioned about half the market from your traditional type 1-2 type cement to the Portland limestone cement. And we see the US, we expect those changes to be coming here potentially a little bit faster. So if we could take a time machine 10 years to the future, I'd say the US will likely be in excess of 50% Portland limestone cement. So even if you don't want to use it now, just be warned that you're likely going to see it in the future. Now that 8.9 million tons of CO2 that could have been reduced, that's equivalent to taking 1.7 million cars off the road each year. 38,000 homes energy use for the year would emit a similar amount of CO2, or the carbon sequestered by 10 million acres of US forests. So that gives you an idea of exactly how big the scale of something as trivial as putting a little extra limestone in the cement can be. So in Illinois has had type 1L approved in the DOT spec for some time. I believe it was right around 2012 or shortly thereafter that it went into the spec, but the PLC has not been in the market as an available option. That said, in 2014, the tollway did do some composite joint plain concrete pavement and completed that project with Portland limestone cement. Roughly 70,000 cubic yards, and the PLC pavement, basically it performs very similarly to the type 1-2, and they had no issues during the construction, and they've collected some data on that. So that's a project that's in place and you've been using for 6 years now and may not have even been aware of. There is currently a drive to get PLC used in Illinois. We, as St. Mary's, currently have limited quantities of type 1L available in the Illinois market. But as Marvin said, there are logistical considerations that affect how we do that. So we can't supply the 1L everywhere. Basically anywhere accessible to our Chicago terminal could get it. But if you had a job out west or downstate and you pick up from, say, our Dixon plant, we wouldn't be able to supply it for sure. However, if that was something you were interested in and you contacted us, it's something we could discuss whether it's logistically possible to meet the demands of your project. And we would be more than happy to work with our customers to spread the use of the PLC and help you guys achieve your goals. So with it in the market now, we are doing other projects with a few producers and gathering information. And unfortunately, we don't have that information and those projects aren't finished and we're in the early stages. But over the next 6 months, more and more information is going to be available. And frankly, it will become more and more widespread for usage and more easy to obtain in the various market areas. So what role can you play in embracing the PLC? Basically, if you're a developer, just bringing up the fact that you want to reduce CO2 and do those things is a good first step. It helps build awareness, and even if there are hurdles to it, it does drive us towards where we want to be. If you're an engineer, educating your clients you work for that the technology is available to reduce the CO2, and this product can be used in basically any application that you can complete with current type 1-2 technologies. And the biggest hurdle right now for PLC is specifications that do not allow for PLC. Marvin gave you information on how to see if it's approved for your the specification you're working with and what could need to be changed. Basically, that is the biggest hurdle when it's not in a specification from our perspective, because as suppliers to the market, we need to make sure that people can do the work they need to do. If we were to basically go and say, we've made a corporate decision, we're switching all our type 1 to type PLC, there would be projects that wouldn't be able to be done just because the specifications are outdated. So when you guys do work on projects and see specifications that may not include the C595 cements, bringing that up helps get those projects up to date so that this product can be more widely used. Also, as Marvin mentioned, if you are interested in PLC, the first step is to ask your concrete supplier if they have PLC. And if they don't, you can have them reach out to their cement supplier, and we can help them get the product into their silos so that it can be used for the projects in your area. And we've listed again the IRMCA member cement producing companies that you might be reaching out to. So in conclusion, basically type 1L, it's going to reduce your embodied carbon by about 10%. It's an engineered product that is engineered to meet equivalent performance of the type 1-2 product you're used to. When you're thinking about a switch from type 1-2 to PLC, the best way to think about it is just how you would think about any other cement change. For instance, so I'm with St. Mary's, Marvin's from Bootsy. If you were switching between the cement supplied by each of our company, you would have to make minor admix adjustments, and the same is true for PLC. So it's really nothing that the plants don't already, or the concrete producers don't already deal with. And while I said it's an equivalent product, there are favorable benefits. For instance, in the downtown markets and paving applications and things like that, where early strength is a concern, PLC does have some performance benefits that may help expedite schedules by allowing the work to get done faster. Hopefully, this information helps answer a lot of the questions you may have had that kept you from considering PLC in the past. And we'd hope you'd be interested in trying PLC in future projects. And that's the last slide I have, Theron. So I guess at this point, I believe you're going to open it up to questions.
Yeah, thanks, James and Marvin. Great job with your presentations today. We do have some questions we're going to get to. First question is it necessary to use more high-range water reducer to maintain workability when increasing blane and holding the water cement ratio constant to get the equivalent strength performance?
I can answer this. Typically, your admix dosages will change slightly. In the trial batches and work that we've done with some of our customers, typically the water reducer dosage does go up slightly when switching from your type 1-2 to your type 1L or PLC. So there may be a slight increase, but at the same time, you're still using the same products in the mix. So it's just an admixture adjustment. And frankly, your concrete producers will be making adjustments daily based on weather conditions and other factors as well. Anything to add on that, Marvin?
No, actually, I was thinking the same thing. Actually, some of the 1L testing I've seen, some of it, we didn't see any additional water demand. But in general, I would agree with you, James. I would, if I was a ready mix producer and I was using it tomorrow, I'd evaluate that on a mix by mix basis and make sure that we're still apples to apples.
Perfect. All right, the next question is, how does it perform in surface resistivity compared to type 1, type 2?
Hang on just one second. I've actually got a slide that may address that. While I'm pulling that up, I will say that for all intents and purposes, they are roughly equivalent. Surface resistivity.
Yeah, we've not seen a lot of massive changes between our normal type 1 or type 2 cement and a 1L. They've been pretty similar.
Yeah, I am not finding the slide I thought I had, but overall they're very similar. I guess from memory, typically your surface resistivities, I believe your standard concrete is typically on the order of 2,000. When you get into lower permeability specification requirements, those set points are rather drastically reduced. I believe it goes down to like 1,200. before you get into the lower permeability mixes. For the PLC, the particle packing helps. So it's very similar, but by 28 days, you might be, a percent or two different. And again, it's going to vary depending on whose cement it is, but a 2% change there is not enough to impact your performance testing.
All right, the next question. Since the manufacturing of PLC uses less energy, is the cost per cubic yard less than normal type concrete?
I don't know if we should answer. Well, it's going to produce less CO2 per ton of cement, is the right way of putting that. But it will require longer time in the finish mill to grind it finer. So I don't know if we should even comment on price, should we?
Well, I think you could be generic. I guess what they're asking is if the market switched to Portland's limestone cement, is there a drastic cost, right? If you had something like a microsilica, right, we know that adds a bunch of cost. Are we typically seeing that they're a small percentage, about the same, or?
So I'll take a stab, and again, since this is getting close to antitrust concerns, but I don't believe it crosses the line. So comparatively speaking, as Marvin said, there is additional grinding that essentially brings the two products near parity. In one plant, they may save a little money, but in another plant, they may actually use a little extra money. It depends on energy prices and whatnot. So the biggest thing where that would make a difference, and it's not applicable in the US, and I'll say yet, I know in Canada, there is a difference in perceived price to the final customer because while cement prices between the two stay the same, Canada has a carbon tax. So you will pay a higher carbon tax on the standard ordinary Portland cement, and you would see a slightly lower tax on the Portland limestone cement. But again, that's not in the US.
And the person who wrote that said something about energy. Really, what we're achieving here is reduced CO2 per ton of cement. And that is one of the bars that we're being held to as a company, not only us, but all the cement companies. And that's the benefit for us as a country, is we would be producing less CO2 per ton of cement utilized.
Okay, good answer, guys. Is bleed reduced with the finer grind, higher bling?
You might see a little bit of a reduced bleed. It may not be a lot, but this is minor change. But yeah, I see what you're saying. It might reduce your bleed a little bit. Well,
Okay.
James, have you seen that too?
Yeah, I would say I agree with what you said. You may see a slight reduction, but not anything significant. The only caveat I would make there is that's for your standard mixes. When you get into more refined mixes with significantly lower water cement ratios, it may become more of a concern. And when I say lower water cement ratios, I mean, if you're in the 3:2 water cement ratio, you don't have as much free water to go around. So those would be the cases when it would be something you'd want to at least verify with the trial mix, though trial mixes are always recommended. We did do a trial batch with one of our partner companies last summer, and frankly, the finishers on that, and that was essentially a sidewalk mix. He actually preferred the feel of the 1L, even though initially he was concerned because he didn't see as much bleed come up. The water is still there. It's just fighting a little harder to get through those finer particles.
Okay. Then we got one more question before we call it quits. This is from a person in Wisconsin, in the Wisconsin market. And his question is, is the 6 months to a year window accurate for all cement suppliers to receive type 1L cement?
I would say no. And I would say even among, internally for St. Mary's, that number differs depending where you're at. And ultimately it comes down to logistics. Just like concrete producers have to worry about silo space, we have the same problem on our end. Frankly, we were hoping to get product out sooner last year than we did, but we had to change the configuration of the supply lines at some of our silos so that we could essentially transport from one silo to our loadout so that we weren't disrupting the normal flow of our product. So I would say if you're in near a major city, I would think though that 6 month time frame is probably pretty close to accurate.
One friendly amendment to that. This question was from Wisconsin, you say?
Yes.
Okay. Here's a friendly amendment to that. Correct me if I'm wrong, but the vast majority of the customers in Wisconsin pick their cement up at terminals. Would you all agree with that for the most part? Because I don't think, is there a cement plant in Wisconsin?
Not that I'm aware of.
That's my point. So, who would be the first customers to see this material? The customers that live close to a cement plant. Okay, because the chances of us, the first silo we're going to free up is a cement plant. And then as we go to terminals, those will be addressed on a gradual basis, so to speak. Well, in Wisconsin, there's no plants. So now I know that there's plants close to Wisconsin, of course. So my point is, they would have to be picking it up, but most likely at a terminal, depending upon where they are. So some areas, you see where I'm going with this. Some areas are going to be slower to make this available than other areas. If you happen to live across the street from a cement plant, your chances are very good that you're going to be one of the first to see it.
Yeah, he did specify it's a terminal pickup in Wisconsin. It would be a terminal.
Okay.
That's all we have for questions for today. I'll be closing this out in 1 second.
Thanks, Theron. Thanks, everyone.
Thanks, James.
Hold on, we still got another minute here. No, don't be leaving us yet. I know everybody wants their green beer.
I'm an hour ahead of you, so I get to drink it first.
So just in closing, we wanted to share that thank everybody for coming today and staying on. We hope this was very informative for you. The concrete industry, as you heard Marvin and James speak, are very interested in moving from type 1, type 2 to a Portland limestone cement. Part of that has to start with the engineering community altering their specifications. So that's kind of part of the education we want to share with you today. We want to also advertise our next webinar, which is next week, March 25th at 12 o'clock. It's a joint conference with the Ohio Concrete Association. The topic is how to design industrial and light duty asphalt parking lots. We have Mike Harrell, principal engineer with Applied Research Associates. And we have Mike Ward, operations manager for the Rabine Paving Group. Registration will open on Friday, March 19th. We also want to mention we do have a free engineering assistance. We have over five pavement engineers at our national group. If you as an engineer need help changing your specifications, designing any kind of concrete technology, we help for free. These pavement engineers talk about this stuff in their sleep. They're experts at it. So again, it's free assistance. You just have to give me a call or an email. And we are on social media, LinkedIn, Facebook, and Instagram. And with that, again, that's all we have for today. I'd like to thank everybody for coming and looking forward to seeing all of you on the 25th.